get started. It's my pleasure to introduce next speaker, Ping Xu again. We'll speak about this time mathematical. So he will talk about his work on shift-derived Poisson manifolds.
Thank you. Thanks again very much. Thanks. Only organizer now, a little apple coffee. No, thanks all the participants, all the others here. So now after a cup of coffee, I wake up. I really appreciate that. Really good pleasure to be here. And after almost 2 years, 2 years lockdown, and my first conferences, I really was so excited. I constantly email. Is this conference going on? Is this conference on? Right? Right? Is it like a constant email? No, yeah. Well, where are you going to have conference? Well, no, I'm the only one keep asking if we're going to have conference. All right. All right. Thanks again. Thanks very much. Also, I apologize that I have to. I changed my title last minute. This is my new title. And I felt this fits better with today's sections. And so I'm going to talk about shift-derived Poisson manifolds. It's based on some joint work with a different piece of work with, well, I don't know, Roger, how to pronounce. I only, yeah. Anyway, so.
You changed your title by left truncation.
Exactly. So most of my talk, it's in some sense, it's kind of a service talk. It's a talk of not so much new mathematics. I put it this way. I just gave some examples. I don't want to get into too much of a credit of those. It's things. It's just I found it probably it's also important to give some service to do some of. I know there's a lot of things going on. Derived symplectic geometry. So must want to talk about derived symplectic Poisson geometry, and we need to talk the PTVV. And Tony Pentoff, Turan, the other was a Vec. I don't know how to say Vecchier and a Vasosi. All right, you guys know better. So all right. So they around 2011. So they loaded this really landmark papers, the paper on this derived symplectic geometry. And I think the motivation is very different for people in algebra geometry, and they want to study those basically n-shift symplectic structure, which is a generalization of symplectic structure on the smooth variety of schemes to the arcing stack and the derived arcing stack. Those I think that's the ideal. And basically they want to deal with those probably the study problems. They want to derive module stacks. Derived module stack, for instance, derived module stack perfect complexes of color BL varieties. Do not ask me those terminal. I just swallow it and spit to you. I do not know any of the terminology. I'm trained as a differential geometer. So what I'm going to talk about is of a infinity context.
I guess for like you could also do derived Poisson black who did derived Poisson with that. So.
Derived.
Well,
oh.
Put a C in there for Poisson as well. It's collect, but you should be getting towards derived.
Oh yeah, but I mean derived. I'm talking about CTPP. All right. Well, I mean. This is not meant a survey on derived symplectic geometry. All right. So I just I already made it clear. I'm talking about something I'm familiar with. All right. So there's a lot of lists of paper I need. If you want me to give a list, I'm going to spend my 40 minutes on this. And can I move on? Can I move on? All right. Good. So first of all, I'm not going to survey. I'm not an expert, and even though I'm very excited all the development, I keep time learning all those, but I'm not really. It's not on purpose. So I'm talking about infinite context, and let me remind you, very classical in Poisson geometry. like two type of Poisson algebra. That everybody would know. I think one is in the even case, one is called Poisson algebra or Poisson manifold, and which is basically, and that's what we learned in simple geometry. First examples, right? This is a Poisson, and then the other one is nowadays called Scoton algebra. And basically, it's a Gerstenhaber algebra. That's also, I learned when I was a graduate student to study this in Gerstenhaber algebra. No, Scoton algebra, the Scoton bracket. And that appears to be normally, that's what I learned when I graduate students on here, which is a symphony function. If the modern way of writing this, I'm learning the terminology is a section of this, minus this part. All right. So shift the minus one. So that is the, you consider the minus. That's the, I can see Dimo. It's okay, Dimo? But, okay. What? Yeah, so those are the very classical M's ordinary manifold. And well, in 2Z2 grading, I must say some foundational work by Tab, and he's crab again. I do not know how to pronounce it. Harvey. KH. Sorry. Oh, KHU. I'm sorry. All right. All right. Please forgive me. What? They call high. You look at the paper. This is like which year is a high homotopy. Which year was that? 2008. 2008. Yeah, I don't have a okay. But yeah, that's a high home. And they define, so basically it's they define an extension of this to the Z grading. And now you can see all the homotopy. So they have a Poisson and also Scoton algebra. You call homotopy Poisson, homotopy Scoton, something like this, is it?
The algebras themselves existed much earlier than that, but in this paper we introduced a high symplectic version. So we have how to say homotopy symplectic.
Yeah. So when did you have this homotopy Poisson, homotopy Scoton algebra? I think that's what I learned from your paper. Maybe this is not the recent. Oh, that's before. All right. Is that by you or by both? I don't know. So it's could be. What before the homotopy Poisson, high homotopy Poisson? Is it by you or what?
Well, I think it existed in the air, but at least, people were suggesting different kinds, different homotopy analogs of Poisson algebra, and so I simply recorded one of them in my paper of 2004 about the high derived brackets. And so the main S infinity and P infinity, and then there introduced P infinity. P infinity algebra is the same name. So I guess I'm not sure about the notation, but S infinity and P infinity were introduced just a construction in my paper on high derived brackets. And Alberto has concrete about the same time. I think he introduced P infinity as a name. And concrete example of P infinity.
I need to change my major to mathematical history. Well, that's what I'm doing. I'm not looking at the time in there. I mean, It's if I'm in Europe, that's more or less I'm looking at it. I'm in US, so it's different. But it's I'm looking at now. It's a retirement.
People complained about P infinity.
What?
Because P infinity, well, for us means just the Poisson bracket becomes L infinity, but the algebra structure is strict. Exactly. They say that P infinity would mean that also the algebra structure is appromotive. They didn't like the date, but. Yeah, for us, that's better.
All right. So if I want, so can I move on because I only have like 40 minutes or so. So it's sorry so shifted derived Poisson. If you want a short introduction, is exactly just see what this the Z2 grading change to Z grading, and that's it. So that's if it's short. That I mean. I'm not talking algebra. Let me say again. I'm not talking about geometry. This is a shift. This there. I do not understand any terminology. For me, I retried because I'm not. The thing is, the problem is that I look at it. I cannot go back again. You know, I just suggest all the graduate students. I look at it. I'm too old to study Harshon. I never learned the Harshon. I never studied Harshon. That's the whole problem. So if I study Harshon, I will be able to talk about this. At least I never studied Harshon. It's hard for me to go back. So I'm talking about infinity and algebra structure here. All right. So let me remind you, as I said, I read kind of a service talk. What is a Poisson algebra? It's very. I just draw the diagram. I think I got inspiration from Davey yesterday. And let me draw some picture. What is a Poisson algebra? Poisson algebra have two structures. Commutative algebra, right? And Lie algebra. And then they got compatible. It's the Leibniz rule, right? So what is a shifted? Derived. Well, has two components, which is a Z-graded commutative algebra. And second component, instead of Lie algebra, you have an L infinity algebra. But now you don't want an infinite algebra. With infinity, you always kind of shift, right? So shift infinite algebra. And nowadays, I also play shift infinite algebra. Yeah, but when you do infinity, infinity one is much better to use instead of infinity.
And is it the same as graded infinity?
Graded infinity? I don't know. Shifted is like a. I got to it. I got to P infinity. I mean, it's a shift. You can shift a different degree. Okay, okay. So shifted, let's say shifted, let's say K shifted, all right? So K shifted infinite algebra. And now they have a compatibility condition. And that's the Leibniz rule. Just please forgive me to be precise all the signs, but that's give you an idea. What is it? Yes.
But is the Leibniz rule in each of
Yeah. Whatever you can imagine. Yeah, exactly. Leibniz rule. Yeah, exactly. Now, what is a Poisson manifold? That's what I teach when I teach my graduate student. What is Poisson manifold? I teach a graduate what is a Poisson algebra first. What is a manifold? It's just smooth manifold. The algebra function, whose algebra function is Poisson algebra. And that's exactly the same thing here. So what is a shifted So now a little bit more precise, okay? Okay, shifted, derived, Poisson, manifold is a Z-graded manifold such that C infinity M is a shifted, derived Poisson algebra of degree minus k. And so here I'm extremely careful with the degree now. So I'm extremely careful. So degree is correct. So shift the k is the terminology. All right. So this is a k shifted as a k. Yeah, I think this is correct.
You're not constraining the algebra to be concentrated in non-positive degree? Right?
What?
Are you constraining the algebra to be concentrated in non-positive degree, or just allowing it to be unbounded?
But this is a so degree is a k shifted means
I'm talking about the smooth function.
smooth function. It just because M is a graded manifold, C infinity is a graded algebra. So have a grading there. This has become having this two condition.
Okay, so you're not saying it has to be non-positive degree. You're not saying that the algebra has to be concentrated in that positive degree.
I don't know if I understand.
You're not saying that the algebra is concentrated in non-positive degree. It could be unbounded.
Both positive and negative degrees occur.
No, the algebra have a Z grading there. No. Any. And a lot of example. Actually, what I'm going to show you is they have a both. Yeah, they have a both. Yeah. What this is like one example. It's like kind of examples. So that's what. Yeah. And any other questions? So let me give you another definition. More again, when we talk about Poisson manifold, Poisson geometry, you have one definition use this, another definition because it's a Scottern bracket equals 0, right? Scottern bracket pi by vector Scottern bracket equals 0, and so there's an equivalent definition I learned more or less from John Poisson. Which is equivalent. If you do the exercises, it should be same thing. I'm not trying to. All those it's I'm not making big fuss of this. So it's just equivalent writing down using bivector fields or whatever the polyvector field. But you need a little bit careful about the Z-grading manifold. And you have shift the tangent bundle. I think my degree is correct. I have 2 degree shifting here. Tangent bundle shifted by n+1, and L is weight. It's a weight. So let's call this poly L Mn. All right. So just the L, whatever multi-vector fields of n. All right. With so and then T poly putting n here, shifting degree, maybe putting head with a completion, and that would be just well maybe of those T ML. So basically, you need to take care of shifting. And now, what is this? Is what are those things? You look a little bit carefully. What I wrote down. Those are the here. The symmetric tensor. Oh, I think it should be section. Sorry, right? It should be section with this. Section with this. So what are they? Those are the symmetric tensor of TM shifting by this. So those are the polynomial function on the cotangent bundle. Polynomial function on the cotangent bundle. So those are just the another way you can think it for people in this audience. It's pretty. We see this a lot in graded geometry. It's just shift function, and this is something also I learned from Tad. And some completion of this function of this polynomial. And here you have this is sympathetic manifold. You have a Poisson structure. You have bracket here. So you do have a bracket here. So this is a graded Lie algebra. So you have a bracket. And this is like a place the rule of like Scott and bracket when we define Poisson algebra. So what is the now? I gave you equivalent definition. What? Just you can go to infinity or whatever because the formula, yeah. Yeah, maybe that's what I always that I always I don't know what is the right notation. I have a problem. Is you write direct product instead of all right, because I saw direct products, then you can you just have infinity term. But now, if you look at so what is the and so what is the okay shifted derived Poisson is equivalent to and pi a DG manifold. And a Moyakata element. I don't know, I'm taking the summation.
What is written there?
What?
What is written there the last line?
This.
See?
Oh, I'm sorry. I need another coffee. Yeah. So those are the pi L are those you have higher order, and with the bracket is this bracket exactly here. This coming from this. Yes.
If people who talk about it, they have something more general than G manifolds, no?
Yeah, well, I don't know. I don't ask me because I do not talking about the algebra because those sheaf were derived. I don't know those. I do not. I don't know. I'm just talking about the in symphony context. What could be the derived? And that's what I read. I say this. Yes. Very good question. I think that probably the better thing should call is a homotopy, like what the Tad right? Tad called homotopy, Poisson homotopy, Scott algebra. Those homotopy Poisson maybe the better terminology, but the derived I think we borrowed from.
I think yes. I think there's a confusion to what the adjective derived is applied. So because when we speak about fixed concrete manifold, the graded manifold, so you have just a homotopy, say P infinity structure or P infinity structure, S infinity structure, which is homotopy Poisson. But the question about derived arises when you want to consider manifolds, well, like similar to you do it like derived category in logical algebra. So then to equivalences, maps and equivalences. And as long as this is not discussed, so this algebra plays a little role.
Just to match the terminology of like derived manifold yesterday as well. If it is
What?
constantly a non-positive degree, then it does represent a derived manifold with the shift to Poisson structure in the same way that it's done in derived algebraic geometry. So.
Oh, thank you. Yeah, as Davey says, that's another reason, maybe putting because you want a derived geometry, and which deals with the derived geometry. But the thing is, the derived geometry is still not so well defined in symphony context, in my point of view. So it's a let me answer your question. To be honest, to answer your question, my point of view, what you call derived, my point of view. And I just repeated what I stated for Keeler, my first talk. I'm trying to survive, and this is good. This is good to get attention, and I get like a more audience to come to the talks, and maybe the paper can be like a fashion. So I could my paper may be easier to publish. So
Sorry,
I could write
I
one
just
line.
wanted to ask what kind of maps, what kind of categories they form. For example, can it be just a model category, and this is objects in homotopy category? You mentioned that by analogy with the right category.
No.
that
This one have nothing to do with derived category. What I talked about here. What?
You have your CFO. You have your Tiger mathematics in your paper. Right?
No, I mean this one have nothing to do with derived category.
Okay.
No,
Well,
there is some relation.
There is a relation. I mean, if you embed this a singular Poisson space into a larger smooth superspace, that will carry such a structure, like as in battalion Prakhtin Bukovitsky. So I mean, I think that point of view, this is kind of resolution of the singular Poisson space.
But maybe I give you examples. So maybe that might explain some of very simple examples. Answer, I don't know if it's answer your question or not. So I just meant it. But why is this called derived? Let's say this is the way to derive the intersection. Again, you will call why is it called derived intersection, right? So let me give you one example. Before I give one more example, I want to focus a little bit, narrow down. Instead of shift the K, I want to mention there's two important examples, at least to me, is K0, and now everything is 0. And then you already see this, like Ted pointed out, this is the P infinity of albedo follow. Right, and now I want a more focus to -1 shifted. So that's probably what I'm going to do. So let me give another. What is this definition? Because it seems to complicate. What is minus shifted is? That's what the so a minus shifted.
K to 0 case. M is any Q man?
Yeah, M is any Q man DG, but shifted K is 0. So P infinity, in other words, P infinity is 0 shifted. According to the definition I'm talking about.
So it's not a normal manifold.
No. M is a curly M. M is when I say curly M is it's not the Z graded. Yeah.
Just to clarify, so you have in your P, you already have a term with degree 1. So
where's the P? I don't have a P.
In your pi, so the P but pi, sorry, pi with twiddle.
Yeah.
So, but Q can they just make part of it? So in principle.
Yeah.
So you
So
don't have to consider
exactly.
Q
So
separately.
a very good observation. And the Q actually is pi1.
Yes. that's
So
what
pi
I'm
one,
saying.
and then this become bracket bracket equals 0. The reason I'm writing this is a lot of people like MC. so that exactly the pi bracket equals 0. Yeah, very good.
Unless for some reason you want
No,
to
no.
separate to-
No, it's the same thing. It's the same thing. It's again, it is a way to impress people. Sorry, I'm all the time all the young people trick, which I'm not supposed to, right? You need to teach them science. So
just my guess is that if you have, say, bi-graded case, you may very often have not one grade, not one degree, but several degrees. Then you may subdivide pi further, and then the separation of Q may make sense because
right,
particular weights degrees in particular degree.
Yeah, I agree. We talked about this bi-grading, so we should talk.
So we want to fix one Q and then consider different pi's. But you
Yes.
allow pi1 to be different from 0, right?
What?
Pi1 can be different from 0, right?
Pi1 to be
Different from Q.
no,
From
I
Q,
don't
from
have a
Q.
pi1.
No, from 0.
I don't have a pi0.
No, pi1.
Oh, I'm sorry. No, I'm sorry. This is wrong.
Ah, so that's
No, I'm sorry. No,
okay.
no. No,
okay.
no.
So you
I
don't change Q. You don't change
I'm
Q.
sorry. No. There's a typo. I mean, the L starts with 2. I single out the pi1 called Q. No pi0. No pi0. No,
No, pi1, no pi 0. So pi 0 will give a.
No, there is a pi1. Pi1 I call Q.
Yes.
There is a pi1, which is just a vector field, because the bracket equals 0. You know, with this pi1, let's call Q, and the Q bracket equals 0. That's our vector field. I single that out because I want to call MC. When I call MC, because I want to impress people, because everybody is using MC.
Pi is Q plus pi tilde, and pi commutes with itself.
Oh, can I move on? I don't know what the. All right. So I think this is interesting. I spent a lot of time trying to figure out the sign. What does that mean? I really want to sell this as because it's not a big deal. There's a homework, right? I mean, but it's a good service, really good service to understand all the sign correctly. And so, what is the -1 shifted derived? Well,
No, I mean, there's no saying here.
why? Here or there? F. Oh. Right. All right. No, because I wrote down the Q. Oh, yeah. David, I'm sorry. Let me put more precise. So I forgot the one because I don't know. I got too excited. Sorry. This one. Can I write down here? So pi L is weight L vector Pauli, right? And now use this one. I'm correct. So this is using shifting degree, which I mentioned here. And then you need to shift back using -k-1 so that to get a degree 1. So this is degree 1 element so that you can talk about MC. All right. So thanks very much. But you have whole pulses, formal pulses. All right. But let me say -1 case. And -1 case, that to me is a most interesting because it's really hard. BV other things is and now just pi. And all the degree shifting, very good. So you dispute. So this guy, if you look at this, will be section of M SLTM, and which is just degree L polynomials on cotangent bundle. No, just I think what is it? No, it's not. So, anyways, let's say degree L polynomials of this. So cotangent bundle is symplectic. You have a bracket. So that's exactly the bracket. Yes, tap.
So a quick question, because you actually have Y greater here. So L stands for the total degree.
Yeah.
Or just the
Total degree. No, no,
total degree, not.
I only have one grading. So all the I start with Z grading manifold, and then I carefully write down the
Because
grading.
you put a cell, that's what confuses me. So you put CL at the right hand side. and
You
then
mean here?
Yes, but then.
Here, this definition N is defined as SLTM shifted
But
by M plus
SL
1.
means simply, how to say? A
Symmetric
alpha-
tensor.
Symmetric power, right?
Yeah,
But
symmetric.
then it is not total degree.
No, this yeah, total degree should be whatever I have here.
Yes, but there you use L for total degree or just for like L there. That's
No,
it.
so this is the definition over here.
Yes.
So this is the minus K minus 2 here.
L here, L there.
L is this one, is just that one, is weight. This is have a like bivector field, a trivector field, and what do you call like a four vector? It's just
just a
it's a
fiber
weight.
degree. It's a fiber
yeah,
degree.
it's a white. I call weight. Is that like a? Is that? I think I learned it from someone. I don't know.
You learned from me, but in the opposite sense.
I don't know. I learned it because I have so many experts. I'm kind of afraid of talking
Weight,
about it in
well,
front of so many experts here. So I don't. It's weight. It's
No,
weight.
Well, is it no degree?
What?
Curly M is also a degree, which doesn't play a role.
M, of course, comes to the curly M. When you talk about this degree here, this is graded. M is graded, TM is graded, has a grading, inherited grading, and it shifted. This has total grading.
No, but the shifting is usually only the fiber degree.
Yeah, but I'm talking about the total degree.
But what is the total degree?
The total degree with this guy by the end degree 1. Okay, let's forget about this. Can we move to this one?
Yes,
Can I
let's-
not? Because this is not. Because I'm
Let's let the speaker proceed.
okay. Very good. Thank you. Thank you. Can I just move -1 shifted? It has no degree shifting. All right. So this one there's no. This is just M is Z graded manifold. Here I have a degree L polynomial. You have a Poisson bracket here, symplectic map. And now what is shifting my one is exactly this is the MC equation. So that's what I meant. So exactly same equation. So all right. Let me this one there's no degree shifting at all. And degree, but you need a total degree 1 element. So this is a total degree 1 such that this MC. All right. So let me give you one example, and then how many minutes I have? I suppose it's 20 or what?
15 minutes, 35.
Are you sure? No. I think no. I'm supposed to 25. I'm supposed to finish at 25. So 6 minutes. 6 minutes.
No, 35. We're 10 minutes, started 10 minutes late, so you have 15.
No. I say that we agreement as a cut it. So we've.
Can you finish in 5?
No, but then they got everything. No, I think I cut my talk to whatever period. So supposed to finish by 25. Yeah. No, I think that's what. Well, whatever I can do. Because I traded. I think people are tired anyway. So I just stopped me when 25. I think I traded. I don't want people really listen to talks and less talks. So people are tired. And I think coffee breaks are much more interesting. All right. All right, so where I am. So let me give you one example to answer Yuri's question. Let me start with M is a manifold. And let's take S as one form, a closed one form. And for instance, in David's talk, F can be exact one form of function. And so basically, this is basically a model of intersection derived. So you want to look at the intersection of a graph of this S with zero section, two Lagrange intersection, which is the intersection which is not smooth manifold. So here we do expect this one is still derived the symplectic whatever. So that's what so what is in this case? Because this is symplectic, you need to shift the -1. Still, this becomes Schottland algebra. So shift the -1 and contraction pi2. And this is a -1 shifted. Basically, derived. This is a so what is a function? Yeah, so pi2, pi2 is a bivector field. So I call this M. And pi2 again will be polynomial of degree 2 of T, Tm do. So it's bivector, not a bivector because it's symmetric now, right? So I should not call bivector field. Symmetric tensor, in fact. So it's shifted. So that's -1. You got to shift it. You got a symmetric. You are doing Riemannian geometry, not a Poisson geometry. That's why you do quantization. You get Laplacian. You don't get the Laplacian. Yeah, but I try to skip the. All right. So what is the algebra? And this algebra M. And this one is just the you write down. You can see this is just the Scott Tm, right? But I used to putting stars a huge positive degree because to matching those people derived, they're putting minus. That's exactly I think the right degree. And I think I really told me this should be the right things, not the other way around. Otherwise, this is well, I don't know. This is confused with BD or BV. I don't know. So that is the smooth function, and Q is this guy. It's a degree 1 derivation, which is just contraction, right? It's a contraction. You contract. And that's the Q. So Ray gives you the derivative. That's the, if I forgot about pi2, that's, I think that appears in talk, maybe yesterday talk, maybe in David's talk, number 2. So this is the basic derivative section of two manifolds. It's one's graph and one's zero section. This is a smooth model of derived intersection. Now, what is pi2 is basically, this is a symplectic. You have a symplectic form, you revert it. That's pi2, and put a sign. That's pi2. So that's the one example. So I have 1 minute, which I do not have time to talk. So let's assume we know what are the examples of Poisson manifold. The first example we know as graduates is Lie Poisson. Right? And that's simple. And that's the same thing. So here you would say, what is the example of derived? So you got an infinite algebroids. I have no time to talk about infinite algebroids. In special cases, that's what become Camille and Thomas did. But you can put more general, get infinite algebroids. And giving any infinite algebroid, you can have a Lie Poisson shift 1. So that was, I believe this. So I give you one example. That's what we did. I need at least to talk about one examples. let's say F is a foliation. Oh, I asked Prince for 2 minutes extension. So, so F is a foliation, and I want to ask what is the so the question you want to answer is what is the so the question is what is the Scoton algebra of polyvector field, which is should be basically -1 shifted derived, because you have a if notion on the leaf space, which the correct notion should be stacked, but I give you approximation. So as a space, this should be as a vector space, should be derived and normal bundle wedge. So as a space, so let's NF is a normal bundle. Let's just mix up F and TF, and then the S space is this guy. And now you want to ask what is the structure here, like analog Scoton bracket, right? So you need a bracket. Now it turns out that you need to derive. You go back. You do not exactly Jacobi identity anymore. So assume was so we proved is basically F1 admits it's canonical unique up to isomorphism infinity algebraic. And then using this same thing as the Poisson trick, and therefore the same thing, which I do not have time to talk about, using the shifting trick. So now you can see answer David's question. You have degree 1 - 1 at the both direction, because you really have 2 directions now here, and this is again it's canonical -1 shifted. Awesome. Actually, this is a sympathetic. This should be sympathetic in this case, and that's the example. So I don't have time to write down. It's more or less not difficult. So as corollary, you can see the homology, and which I even this I never saw this. So it's because basically the Ram homology of F with is Gaussian algebra. This is canonical. Because everything that you need a choice. To prove this, you need a choice, but the isomorphic, this is canonical Gaussian algebra. This is a very simple example. So you do not, I didn't find it in the literature. So now 1 minute extension is okay. So I like a chart, I'm getting like a, okay. So I need to like conclude my talk with connection with Keeler. So what I want to mention is I gave these examples as a baby examples, a kind of a toy model. It's foliation because everyone is foliation. In fact, all the construction works for called Lie pair. And Keeler worked on this long time ago. He wrote a beautiful paper, which I wasn't aware of until only very recently. So he called a comma double legal point and the algebra. Basically, you have a morphism. What a Lie pair means, you have a legal point and subgroup point with same base, a pair. So you have a Lie pair, basically, and you have a lead pair. So he construct this double algebraic, he construct double groupoid actually, and we figured out that he already there 20 or 30 years ago, and that helps to understand everything extend to the Lie case, and to get another thing is you want this infinity to homotopy. We know any infinity algebra is a homotopy to DG, right? So you want to see if this, so then those things will be what we did. The Luca is to construct a DG Lie algebra using what CAD dictionary they translate double to get a Lie homotopy to those. So equivalent. So I think I stop here, and thanks very much.
So I mean, your original title, it said quantization. So can you say like what results you have about the quantization of these